Hello everyone, myself Dr. Ranjith Kumar Gatla. I am working as an associate professor in Department of Electrical and Electronic Engineering, Institute of Aeronautical Engineering. Today, we are going to discuss about the dual converter in power electronics. So here, the name itself, it gives the definition, the dual converter. So as we know, the converter means it can convert from either AC to DC or DC to AC, or the converter, it will flow from the load side to, the source to load or the load to source. But here, the dual converter, the name itself says the two converters. Here in the picture, as you can see, the converter 1 and the converter 2, and the converter 1 and the converter 2, we are connected in anti-parallel, and in between the converter 1 and converter 2, we have connected a common load, and the input of the converter 1 and converter 2 also we are giving a common supply. Even though there are two converters, but the two converters having the input is a common supply and the output is a common load which we are connecting. And then when coming to the converter 1 and converter 2, okay, so what the converter 1, whether it is rectifier or inverter. So here, two full bridge, suppose, in the dual converters also, there are single phase dual converter and three phase dual converter. So first let us discuss about the single phase dual converter. In single phase dual converter, we should connect two single phase full bridge rectifiers in anti-parallel, then it will make it as then we can make it as a dual converter. And here, as you can see, in the dual converter, of course, anyway, we are using the two full bridge rectifiers, we are connecting in anti-parallel, and we are indicating the first converter is a converter 1 and the second one is the converter 2. Then the converter 1 will perform as a rectifier, and then the other converter, the converter 2, will perform as a inverter. Suppose, and if converter 2 is performing as a rectifier, then the converter 1 will perform as a inverter. So this is about the basic structure of the dual converter, and this is the actual single phase dual converter, as you can see, converter 1 and converter 2. And why we are going for this dual converter, and what are the main advantages of this dual converter? So when compared to because till now in the previous sessions we have discussed the single phase full bridge rectifier, and as we know, in the single phase full bridge rectifier, we can operate in two regions, right? One is in the, suppose from 0 to 90 degrees, the firing angle of 0 to 90 degrees, we can operate as a rectification mode, and from 90 to 180 degrees mode, the same full bridge converter can be operated as a inversion mode, which means in the rectification mode, the full bridge inverter, the source supplies to the load, and in the inversion operation, when the alpha is 90 to 180 degrees, the load will supply to the source. So same thing, the same concept here we are going to apply for the converter 1 as well as for the converter 2. So by using these dual converter, we can operate in 4 quadrants. Here, as we can see, the 4 different quadrants, and the first quadrant, which means the converter 1 will operate in the first and the 4th quadrant, and converter 2 will operate in the second and the 3rd quadrant. So when coming to the converter 1, first quadrant, the converter 1 will act as a rectifier, and the same converter in the fourth quadrant, it will act as a inverter. Similarly, when coming to the converter 2, in the second quadrant, the converter 2 will operate in the inversion mode, and in the third quadrant, the same converter 2 will be perform as a rectification mode. Then, how these converter 1 or what is the condition to operate the converter 1 in the first quadrant, and similarly, what is the condition to operate the converter 1 in the fourth quadrant, that we will discuss. But the main advantages of this dual converter is it will operate in the 4 quadrants. So based on our requirement, so which converter we should operate and what is the condition to get operate that converter, that we will discuss one by one. So here, as you can see, this is the single phase dual converter. So here, this is the one full bridge converter, and the same full bridge converter, if you connect anti-parallel, then it will make it as a dual converter. And the load in between these two, we have connected the load and the supply of the first converter and second converter also we are giving from the same source. And there are basically two modes of operation of these dual converters are there. One is non-circulating current mode, and the second one is the circulating current mode. Non-circulating current mode and the circulating current mode. Then one by one we will discuss what is the non-circulating current mode and what is the circulating current mode. First we will discuss about the non-circulating current mode. It is very simple. In the non-circulating current mode, one converter will perform at a time. One converter will perform at a time, which means both the converters should not perform at the same time. Only one converter should perform at a time. Either it can be first converter or it can be second converter. But the condition in the non-circulating current mode is, or if only one converter is performed at a time, then that kind of operation or that kind of mode is called as a non-circulating current mode. So that there is no circulating current between the converters, which means from converter 1 to converter 2 or converter 2 to converter 1. Because only one converter is operating at a time. Either it may be 1 or 2. So that's why there is no circulating current between the what is that one converter to another converter. So that's why this mode is called as a non-circulating current mode. Then here I have clearly mentioned, as we discussed just now, the one of the main advantage of these dual converter is it can operate in 4 quadrants. Okay, so here I have just mentioned. So let us consider the alpha 1 is the firing angle of that first converter, and alpha 1 is the firing angle of the first converter, and alpha 2 is the firing angle of the second converter. Because we should not take firing angle for the first converter and second converter is same. Okay, so that's why I have just considered the firing angle for the first converter is alpha 1 and the firing angle for the second converter is alpha 2. Suppose as we can see, the converter 1 can be operated in the first and fourth quadrant. Okay, so suppose if you want to operate the first converter the converter 1 in the rectification mode, which means from the source to load. Okay, the supply is from the source to load. Then the firing angle alpha 1 should be in between 0 and 90 degrees. So if you maintain or if you change the firing angle in between 0 and 90 degrees, then the converter 1 will always operate in the rectification mode, because when you operate the converter 1 for the firing angle in between 0 and 90, both VDC and IDC are the positive. Okay, both the output voltage and current are positive. So here in the first quadrant, both the output voltage and currents are positive. So this is the rectification mode, because the actual rectifier function is AC to DC. So here the AC is the source and DC is the load. So from the supply is from the source to load. And the same converter, if you want to operate in the inversion mode, which means from load to source, which means from DC to AC. Then you have to operate the alpha 1 as in between the 90 greater than alpha 1 is less than 180 degrees, which means you have to operate the alpha 1 in between 90 and 180 degrees. Then the converter 1 will be operate in the inversion mode, which means the supply is from the load to source side. Similarly, because this is non-circulating current mode, so that's why at a time we should operate only one converter. So that's why I'm just taking one by one. So first I have considered the first converter, and if you want to operate the first converter in the rectification mode, then you have to give the alpha value in between 0 and 90 degrees. And the same converter, if you want to operate in the inversion mode, then you have to give the alpha value in between 90 and 180 degrees. That is about the converter 1. Or suppose if you want to operate only the converter 2, not the converter 1. Then similar way here, if you want to operate the converter 2 in the inversion mode, if you want to operate the converter 2 in the inversion mode, here as you can see, during the converter 2 operation, the firing angle alpha, it will be 0 and 90, then VDC and IDC are negative. I mean in a reverse way. Okay, so in between, if alpha 2 is in between 0 and 90, then both the VDC and IDC are negative, so that it will be in the rectification mode. And in between 90 and 180 degrees, then it is in the inversion mode for the converter 2. So from one quadrant to another quadrant, or from one operating mode to another operating mode, if you want to shift, then you have to change the firing angle of the converter 1 and converter 2. This is about the non-circulating current mode. Then when coming to the circulating current mode, in the circulating current mode, two converters will be in an on condition at the same time. So which means, suppose if the two converters are operating at the same time, then that kind of mode is called as a circulating current mode, because the circulating current is present, are flowing from one converter to another converter. So that's why it is a circulating current mode. So when the circulating current mode will happen? Only when the two converters are operate at the same time, so that the current from one converter to another converter will flow. So which means that type of mode of operation is called as a circulating current mode. Then if you want to operate two converters at the same time, then we should follow some conditions. Okay, so then only the converter 1 and 2 will operate at the same time. Otherwise, we won't get the actual function. Here, the main condition is the firing angle adjustment. How you have to give the alpha 1 and alpha 2? Because in the previous case, anyway, there is no such kind of conditions, because we were not operating converter 1 and converter 2 at the same time. We are operating, if we are operating converter 1, then we are not operating the converter 2. Or maybe the converter 2 is operating. So in that case, we no need to follow any condition for the the firing angle. Okay, so only based on our requirement, which means suppose if whether you want to operate the converter 1 is the inversion mode or the rectification mode. So based on that, we will change the firing angle. Similarly, when coming to the converter 2 also, based on our requirement, we are changing the firing angle, so that according to that we will get the operation, either it is in the rectification mode or in the inversion mode. But here we are going to operate the two converters at the same time. Okay, then what is the condition to give the firing angle for the converter 1 and the converter 2, which means alpha 1 and alpha 2. So the condition to give the firing angle for the converter 1 and converter 2 is the alpha 1 plus alpha 2 must be 180 degrees. So you have to give the firing angle for the converter 1 and converter 2 such a way, so such that alpha 1 plus alpha 2 is equal to 180 degrees. Then only you will get the actual dual converter operation. Either it may be first quadrant or the second quadrant or the third or the fourth quadrant. So here I have mentioned two examples. Suppose here the converter 1 performs as a controlled rectifier. When it will act as a controlled rectifier? Because just now we discussed, okay, if the converter 1 will be act as a rectification mode, okay, when the firing angle alpha 1 is in between 0 and 90 degrees. In between 0 and 90 degrees. And converter 2 perform as an inverter when the firing angle is in between 90 and 180 degrees. 90 and 180 degrees. So, in this condition, both VDC and IDC are positive. Okay. And second way, the converter 1 perform as an inverter when the firing angle alpha 1 is 90 and 180. And similarly, when the converter 2 perform as a control rectifier when the firing angle is in between 0 and 90. So, in this condition, both VDC and IDC are negative. Both VDC and IDC are negative, which means, and here let me explain why we need to maintain, or how why we need to maintain alpha 1 plus alpha 2 is equal to 180 degrees. Okay, so that we will discuss here. Like, as you can see here, first the converter 1. With respect to the converter 1, the output voltage is plus and minus. Okay, but with respect to converter 2, okay, the positive voltage is, here it is plus and here it is minus. Then let me consider the output of the converter 1 is V01 and the output of the converter 2 is V02. Okay, so let us consider here V01 is equal to V max into cos alpha 1 and V02 is equal to V max into cos alpha 2, because we are giving the separate firing angle for the converter 1 and converter 2. So, for the converter 1 it is alpha 1 and for the converter 2 it is alpha 2. And of course here the V01 or V0 equal to, okay, the total voltage V0 equal to V01, which is equal to minus V02, right? Because with respect to converter 1, it is V01 plus and minus, but when coming to the second converter, it is the polarities are reversed, so that's why we can make it as minus V02. So, which means here V maximum cos alpha 1 is equal to minus V maximum cos alpha 2. Okay, so here V maximum gets cancelled. Then cos alpha 1 equal to, here minus cos alpha 2, we can make it as cos 180 minus alpha 2. Okay, so if you simplify this, then you will get alpha 1 plus or minus alpha 2 equal to 180 degrees, which means we are getting the two condition. One is alpha 1 plus alpha 2 equal to 180 degrees and alpha 1 minus alpha 2 equal to 180 degrees. Here the two conditions, but which condition we should follow? So here let me take the second condition. In the second condition, okay, when alpha 1 is greater than 180 degrees, then only alpha 1 minus alpha 2, that you will get 180 degrees. Okay, so that's why we cannot consider this one. Okay, because the condition should be satisfied for all the four quadrants. Okay, not for only the one quadrant. Okay, so that's why we are going to consider the alpha 1 plus alpha 2 is equal to 180 degrees. Right? Then here, when coming to the output voltage equations, Yes. So when coming to the output waveforms here, first we are just operating converter 1 and the next converter 2. Okay. So okay, let us consider this is a circulating current mode. Okay, which means we are operating both converter 1 and converter 2 at the same time. Okay. So the condition to get operate both the converters at the same time, we should maintain alpha 1 plus alpha 2 is equal to 180 degrees, which means alpha 1 and alpha 2 we have to take in this way. Okay. So let us consider first alpha 1, for converter 1. Okay, let us consider converter 1 here. From this output voltage equation, as we can see, it is almost alpha is equal to, alpha 1 equal to, let me consider 60 degrees. So this is 60 degrees. Then here alpha 1 is starting. So then the total, what is that, the output voltage, okay, it is follow the same as like the input voltage up to from here. Okay, but because of the inductive effect, okay, so here the negative current will also flow up until what is that, the next thyristor will trigger, because the same way like the full bridge inverter. Okay, so let me consider here, this is T1 and this is T2 and this is T3 and this is T4. Okay, in the first case and during this one, T1 and T2 will conduct, and then here T3 and T4 will get conduct. So during T1 and T2 you will get the output voltage waveform is like that. Okay, and during T3 and T4 you will get the output voltage waveform as like this. Then if alpha 1 is 60, then alpha 2 must be, you have to take 120 degrees. Okay, you have to take 120 degrees. Or pi minus alpha 1, because here let me consider here this is alpha 1 and this firing angle must be, you should start from pi minus alpha 1. So because this is the negative converter, okay, because the output voltage is minus V0, as we can see V01 is equal to minus V02. So that's why here instead of the positive you are getting the negative cycle. Okay, because the reverse way that you will get the negative cycle. Then of course because of the again inductive effect you will get some reverse voltage also. Then during this time again here let me consider this is T1 and this is T2 and this is T3 and this is T4. Then here also T1, T2 will conduct, and here T3 and T4 will get conduct. T3 and T4 will get conduct. Okay, so this is how you will get V01 and V02. And if you just add these two, V01 and V02, then you will get, because here V0 of T, which is equal to V01 plus V02. If you add these V01 and V02, okay, then you will get the actual, what is that, the circulating current output. Okay, so which is like this. Okay, so this is about the output voltage waveforms for the dual converter. Okay, so in both way we can operate this dual converter. Okay, either converter 1 independently or converter 2 independently, or both also you can operate based on your requirement, whether you want to operate in the circulating current mode or the non-circulating current mode. So according to our requirement we can operate this converter. But anyway, more or less in the circulating or non-circulating current mode, so the converter 1 output voltage waveform is like this and the converter 2 output voltage waveform is like this, because in the both the cases you will get the different voltages, right? And when coming to output voltage, then as you can see V0 is equal to V01, that is equal to minus V02. This is the output voltage of the dual converter, right? And here as you can see, this is converter 1 is in the rectification mode. So the converter 1 in the rectification mode, Okay, when the converter 1 will be in the rectification mode, when the alpha 1 is in between 0 to 90 degrees. 0 to 90 degrees. And the same converter 1 in the inversion mode from 180 to 360 degrees. That's why here is in the inversion mode, because in the negative way. And in the same way, suppose if the converter 2 will operate in the rectification mode, then you have to operate it is from 90 to 180 degrees. 90 to 180, then the converter 2 is in the converter 2 will operate in a rectifier mode. And again from 0 to 90, okay, so this will operate as a inverter mode, the converter 2. Okay, so in this way also we can explain the dual converter operation. Then we will go for the three-phase dual converter. In the three-phase dual converter, of course, more or less the structure is same, but instead of the single-phase full converter or the full rectifier, here we are using the three-phase full converter or full rectifier. And these three-phase full converters or full rectifiers, we are connected in anti-parallel. Again, here also V0 equal to V01, which is equal to minus V02. And we have already discussed, here for our understanding, so I have taken the operation when alpha is equal to 60 degrees, because as we know, the three-phase output voltage waveforms are always not same, will change with respect to the firing angle. So here, that's why here let us consider for alpha is equal to 60 degrees. Okay, so what is the output voltage and output current waveform? So which means alpha 1 is equal to 60 means then alpha 2 should be 120 degrees. So here the first waveform here which is representing, this is V01, and here this is the second waveform is representing V02. So the V01 waveform is same like the three-phase rectifier. Okay, so and the three-phase rectifier, as we know, the output voltage waveform is like this. Okay, so either we can take it from the phase voltages or the line voltages. Okay, so this is VBA, VCA, VAB, because which means why here it is VBA from 0 to here it is, let us consider 60 degrees. From 0 to 60 degrees, only the phase B and phase A are conducting. Okay, so that's why VBA is equal to VB minus VA. Okay, and in the second, in this duration, okay, this is VCB, which is nothing but VC minus VB. Okay, which means the thyristors in the phase C and phase B are only conducting. Okay, so in phase A, all the thyristors are in the turn off mode. So that's why here during this time we are getting only VCB. Similarly, again here VAB is equal to VA minus VB. This is VAB. This is about V01. And when coming to the V02, as we know, V02 is equal to minus V01. So which means here during during the first 60 degrees, here we are getting VBA. Okay, this is for V01, and V02, then you will get VAB. Instead of VBA, you will get VAB. So here VBA means VB minus VA, and here it is VA minus VB. That's why here the waveform is VAB only, not VBA. And similarly, here VCB, here it is VCB, but here it is VAC. And similarly, here it is VAB, so here it is VBC. The same way, because V01 equal to minus V02. So if we get one V01 waveform, then the V02 we can easily draw, because already we know what is VA and what is VB and what is VC during 0 to 60 degrees and 60 to 120 degrees. Okay, and 120 to 180 degrees. Okay, so all these modes we know the value, I mean the equation for VA and VB and VC. Okay, then here VBA means 0 to 60, then VB minus VC, and here VAB means VA minus VB. Something like that we can draw. And then the actual load voltage V0 is equal to V01 plus V02. But here, as you can see, the magnitude of V01 and V02 at every instant is different from each other. Because you see, suppose at this particular instant, let me take at this particular instant. Okay, or let me take at this particular instant. So here the V01 magnitude is this much. Okay, and but V02 magnitude is less than the V01. Okay, and when coming to here the V01 magnitude is less than V02. Here V01 magnitude is greater than V02, but here V01 magnitude is less than V02, which means the magnitude of V01 and V02 is different at every instant. So that's why, okay, so when you add V01 and V02, you won't get 0. If it is same, then because V01 is equal to V0 minus V02, okay, so that's why if you add these two, if you take average, then 0. But here at every instant the V01 and V02 magnitudes are different, so that's why here the load voltage is, you are getting something like this, some pulsating DC. This is about the 3-phase dual converter. So then let me conclude about this dual converter. Okay, so when coming to the dual converter means, here the name itself, it says the 2 converters, and here if the 2 converters are the 2 full bridge converters and the 2 full bridge converters are connected in anti-parallel with each other, then it will be treated as a dual converter. And the dual converter, the input is same source and the output is also connected to the same load of these 2 converters, because we are connecting the 2 full bridge converters in anti-parallel. In between we are connecting a common load. That is the structure of the dual converter. And there are 2 different operating modes of the dual converter. And before that, the main advantage of the dual converter is we can operate the dual converter in the 4-quadrant mode, either in the first quadrant or second quadrant or third quadrant and the fourth quadrant. So based on our requirement, then how the dual converter can be shifted from first to second or second to third or third to fourth by changing the firing angle. And here for the converter 1 and when coming to the operating modes, there are 2 different types of operating modes. One is non-circulating current mode, another one is the circulating current mode. And the difference between the non-circulating and the circulating current mode is, if the 2 converters are operating at the same time, then it is a circulating current mode, because the current is circulating from one converter to another converter, because the 2 converters are operating at the same time, so that's why it is a circulating current mode. And in case of non-circulating current mode, only one converter should operate at a time. So there is no flow of current from one converter to another converter, so that's why there is no circulating current flowing, so that's why this is the non-circulating current mode. And when you are operating in the circulating current mode, then you should operate both the converters at the same time. But if you want to operate both the converters at the same time, then you should follow one condition, or you should take the alpha 1 and alpha 2 such that alpha 1 plus alpha 2 equal to 180 degrees. You have to choose the alpha 1 and alpha 2 values according to alpha 1 plus alpha 2 is equal to 180 degrees. Then only you will get the dual converter operation. And how we are getting the alpha 1 plus alpha 2 is equal to 180 degrees? Because as we can see, V01, which is the converter 1 output, and V02 is the converter 2 output. Okay, then V01 equal to minus V02, because the configuration itself, it is an anti-parallel, which means here it is positive, then it is negative, and here it is negative, then it is positive. So if you take V01 as a reference, then V02 is minus V01, because the polarities of the output voltage is opposite with the polarities of the V01. Okay, then when coming to the 3-phase, the same like the single phase, but the output voltage waveforms are totally different from the single phase, because already we have discussed the three-phase rectifiers, okay, how the output voltage of the three-phase rectifier and how we can draw. So the same way here also, I mean, first suppose if you get V01, then automatically you will get the V02, because as we know V01 is equal to minus V02. So which means here V01 is, if you take a particular interval from 0 to 60 degrees, in this 0 to 60 degrees V01 is VBA, then V02 should be VAB. Like that you will get. Then finally, if you add these two, then V0 is equal to, you will get the load voltage like this. This is all about the three-phase dual converter. In next class, we will discuss the other topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.